What we're going to be learning about this week are types of chemical bonds. And to understand the different types of chemical bonds, we need a little bit of background information first. We should already know what a compound is, but just in case we've forgotten, here's a little bit of a refresher. A compound is a substance made of the combined atoms of two or more elements. When you put two or more elements together and they're chemically bonded, then you've made a compound. Some examples of compounds include things we're pretty familiar with, like water, sodium chloride, which is table salt, and carbon dioxide, a gas that we're all worried about with global warming. Another piece of background information that we'll need is the ability to read and understand a chemical formula. A chemical formula tells what elements a compound contains and the exact number of the atoms of those elements. Chemical formulas are the things that I just wrote down as our examples of compounds. You could look at those chemical formulas and determine how many of each atom is in that formula. How many hydrogens are in the water molecule? Well, you'd look at the number next to it and you'd say 2. How many oxygens are in the water molecule? There's no number next to it, so there would be 1. If you look at sodium chloride, there's 1 of each, 1 sodium and 1 chlorine. And if you look at carbon dioxide, there's 1 carbon and 2 oxygens. Let's look at a few more examples of formulas of common compounds. So we'll put a title up here, Some Common Compounds. Again, we're using these as examples of formulas and how to read them. We're using them as examples of compounds. First, here's one that everybody probably has in their kitchen, and its common name is vinegar. Vinegar also has a chemical name, and it goes by the term acetic acid. Now that's not something I expect you to know at this point, but we should be able to read its formula, HC2H3O2, and decide what are the parts of that formula and how many of each are there. How many hydrogens are there? Well, if you look at it, there's 1 here in the front and there's 3 here in the middle. So there's 4 hydrogens altogether. 2 carbons and 2 oxygens. That's the kind of information that you can get from a chemical formula. Let's look at another one. Over spring break, I'm sure everyone was wishing that they were sitting on some silicon dioxide on the beach. Maybe some of you actually were. And the formula for silicon dioxide is SiO2. So again, we don't really need to know the chemical name at this point. This part is not really what we're concerned about. What we need to be able to do is read this formula right here and tell how many atoms of each kind are in that formula. 1 silicon and 2 oxygens. Let's look at another one. If you ate too much Easter candy, you might have been plagued by stomach acid or heartburn. Stomach acid goes by the chemical name hydrochloric acid, and its formula is HCl. So when you look at that formula, there's 1 hydrogen and 1 chlorine there. Let's do one more. All of that Easter candy was probably made partially from cane sugar. Cane sugar goes by the chemical name sucrose. And in fact, anytime you see that ending, that OSE ending, that probably means a sugar, some kind of sugar. And its formula is C12H22O8. So in this formula, there's 12 carbons, 22 hydrogens, and 8 oxygens. Now that we've had a little bit of practice at reading chemical formulas, we're going to put some labels or some vocabulary words to the types of information that you can get from them. So we'll put a new title up here, Parts of Chemical Formulas. We'll look at a couple of formulas specifically and label the parts of those formulas. First, we'll start with one that we're all pretty familiar with. H2O, the water molecule. The little 2 that you see at the bottom, this one right here, tells us that there's 2 hydrogens in this molecule. That part of the formula is called a subscript. It's called a subscript because it's down below the rest of the numbers. That's what that prefix means. SUB usually means below. So a subscript is down below the rest of the letters or numbers. And it represents the number of atoms in a molecule of a particular element. So just like before, we look at that formula and we know that there's 2 hydrogens in that formula. In a couple of weeks, we will start to see numbers out front of our chemical formulas. And those numbers give us information as well. Those numbers, the big ones that are out front, are called coefficients. And a coefficient represents the number of units of each substance. So the number out front would tell you how many water molecules are there. And in this case, there would be 2. Let's look at one more example of the parts of a chemical formula, and this time we're going to have SO4, and then we're also going to have a -2 up at the top. So what are the parts of this formula? Well, we've already talked about one of them. This 4 down below is a subscript. And remember, the subscript tells you how many of that kind of atom. So there would be 4 oxygen atoms in this formula. The other number, which is our new one, right up here, is written above the line of the rest of the letters and numbers. So this is called a superscript. When you see a superscript or a number above the line where the rest of the letters are, that represents the charge of that atom or formula. And another way to say that is the number of electrons that have been lost or gained by that substance. The number of electrons that have been lost or gained, and that represents the charge. It tells you how positive or how negative that substance is. And remember, a substance would be positive or negative by losing electrons. And that's going to be important when we talk about the types of bonds in a couple of minutes. Now that we've covered our background information, we can actually get to the lesson for this week. We're going to be looking at why do atoms bond and what kind of bonds do they make. First of all, why do atoms bond at all? Atoms form compounds to become chemically stable. Atoms form compounds to become chemically stable. What does that mean? Chemically stable is kind of a fancy way of saying the atom is happy with its current state, or where it is, or who it's partnered up with. An atom is chemically stable when the outer shell, we're talking about electrons now, just like we did with our Bohr models, when the outer shell is full. So whatever shell is on the outside, whether that's the first one, the second one, or the third one, when the outermost shell is full, an atom is chemically stable. You might remember from doing your Bohr models that the outer shell is typically full with either 2 electrons if it's the first shell, or 8 electrons if it's the second or third shell. So kind of our magic numbers for these are 2 electrons or 8 electrons. When you have a full outer shell, your atom is chemically stable. In order to become chemically stable, atoms will make chemical bonds. So what is a chemical bond? A chemical bond is the force that holds together the atoms in a substance. Something is holding those atoms side by side, and that something is the chemical bond, and a chemical bond is a force. The force that holds atoms together in a substance. There are two main types of bonds that we're going to learn about. The first are called ionic bonds. Ionic bonds are made from ions. That means we need to know what the term ions is. And we should know, because this is something we learned already, but an ion is a positive or negatively charged atom. A positive or negatively charged atom. That means that that atom has lost or gained electrons. When atoms lose or gain electrons and they become positive or negatively charged, if you have one of each, one positive and one negative, then you get attraction between those opposite charges. And that's the force that holds these bonds together. There's an attraction between opposite charges of ions. Just like with a magnet, the positive side of the magnet will attract the negative side of another magnet. So the attraction between a positive and a negatively charged ion is the force that holds the ionic bond together. If you're going to make an ionic bond, you need two types of elements. Ionic bonds occur between metals and nonmetals. Metals are usually the things that make positive charges. Nonmetals are the things that make negative charges. And we're going to talk about how that happens on the next slide. So how do you make ions to form an ionic bond? Let's do an example. And we're going to take for our example table salt, which is sodium and chlorine. First, we're going to start with some Bohr models. So we need to know, for sodium, how many protons does it have? Look at your periodic table. That's 11. How many electrons does it have? Same as the protons, so that's 11. And we don't really need to know the neutrons, but we'll put them on here anyway. Subtract the mass and the atomic number, and you get 12. So let's draw a Bohr model for sodium. We would have the nucleus in the middle, and we could put protons are 11 and neutrons are 12 in the middle of there. And then we would start to draw our electrons. How many electrons can you put in the first shell? You should be thinking 2. We still have 9 more electrons to place, so that means we need another shell. How many electrons can you put in the second shell? You should be thinking 8. So we'll draw our 8 electrons. Notice that I'm putting them in pairs here. I didn't ask you to do that when we started drawing Bohr models, but it is standard to put them in pairs when you can. Okay, let's count our electrons. We have 2, 4, 6, 8, 10. We need one more, so that means we need another shell. And we're going to put one more electron in that shell. Here's our sodium atom. In order to make an ionic bond, the sodium atom has to make an ion. That means it either has to lose or gain electrons. It does that to try to make a full outer shell. So, how many more electrons would it need to make that third shell, this one out here? How many more electrons would it need to make that full? Well, if full is 8, and it's only got 1 to start with, it would need 7 more. That's a lot more electrons. It's going to have a hard time finding 7 more electrons. But its other option is to lose. It could lose electrons to make a full outer shell. And if it were to lose this last electron right here, we wouldn't even need the third ring. And if you take away the third ring, if you lose this electron, lose that electron, and you take away the third ring, we'll just kind of cross that out. Look what happens. The second ring then becomes the one on the outside, and it's already full. So sodium, when it becomes an ion, will lose 1 electron. Then if we take a look at its statistics, right after that happens, if the sodium has lost an electron, how many electrons does it have now? Count them. 10. How many protons does it still have? We didn't change that, so it's got 11. And we could put the neutrons on here even though we don't really need them. What's important is the difference now between these two numbers. Electrons are all negative. So we have -10 altogether. Protons are positive. That means we have +11 altogether. If you were to add those two numbers up, -10 and +11, what would you get? 11 minus 10 is +1. That means the sodium ion has a positive charge because there's an extra proton that's no longer balanced out by an electron. And this right here, this is that superscript that we talked about on the previous page. But what we really need to know from this is that sodium makes a positive ion because it loses electrons to make a full outer shell. That should make sense because if you look at where sodium is on your periodic table, you should be able to tell that sodium is a metal. And metals make positive ions. Now let's look at the other side of our example, chlorine. If you look up your stats on the periodic table, chlorine has 17 protons, which means it has 17 electrons, and if you subtract its mass and its atomic number, we have 18 neutrons. But again, the neutrons don't really matter for this part. Let's go ahead and draw our Bohr model. We would draw our nucleus, and we'd put 17 protons in it, and 18 neutrons, and then we'd start drawing our electrons. First ring, first shell, holds 2. Second ring or second shell, holds 8. Count them and see. How many do we have so far? 2, 4, 6, 8, 10. I need 7 more. That means I need a third ring. Third shell, third ring, and I only need to put 7 in here, so we'll do 2, 4, 6, 7. The third ring, when it's full, holds 8 electrons. So how many more would chlorine need to make a full outer ring? Look at how many are already here. 2, 4, 6, 7. If I want to make 8, that means I only need 1 more. So chlorine, instead of losing an electron, will gain an electron. And you put an extra electron on it, and then the last shell has 8. The last shell is full. That makes chlorine stable. So then let's look at our new stats. We would have 17 protons, 18 electrons, and 18 neutrons, although they don't really matter. What charge would the chlorine end up being then? Protons are positive, so we'd have plus 17. Electrons are negative, so we'd have negative 18. If you combine plus 17 and negative 18, what do you get? Negative 1. That would be chlorine's superscript, or chlorine's charge, is negative 1. The most important thing to take away from this is that chlorine gains electrons when it makes an ion because it's a non-metal. Non-metals will gain electrons, metals will lose electrons. Okay, last step to making this compound. Sodium lost its electron and ended up with a plus 1 charge. And we'll put its electron, we'll just say plus 1 electron. Because sodium had an electron come off, so now they're separate. Chlorine, on the other hand, would like to gain that electron. Chlorine wanted to gain an electron. So where do you think that electron came from? It came from the sodium. The electron that the sodium lost got picked up by the chlorine. And what we have now are 2 ions with charges, Na plus 1 and Cl minus 1. What do opposites do? Pluses and minuses attract. So after all this, we end up with a compound, NaCl. And when we write them together, the plus and the minus cancel each other out, so we don't need to write the numbers anymore. We have 1 sodium for every chlorine because a plus 1 and a minus 1 balance out. Now we're ready to talk about our second kind of bonding. The second kind of chemical bonds that we're going to learn about are called covalent bonds. Covalent bonds are not made from ions, because instead of having 1 electron lost and then gained, these electrons instead are shared. Electrons end up being shared between 2 atoms. Covalent bonds are unique because they can form multiple bonds. That means instead of having a single bond between two atoms, you could have what's called a double bond or a triple bond, although we're not going to get into that a lot. And covalent bonds will form between nonmetals. So we'll list that twice, between a nonmetal and another nonmetal. Let's do an example. So for our example, let's take something simple. Hydrogen fluoride, HF. Remember, hydrogen is a nonmetal, even though it's on the left-hand side of the periodic table. Okay, let's start with some Bohr models. Hydrogen has how many protons? 1. How many electrons? 1. And neutrons is 0. So let's draw hydrogen's Bohr model. We have our nucleus, and we have 1 proton in it. And then we have 1 electron in the first ring. Okay, and on the other side, let's draw fluorine. Fluorine has how many protons? 9. How many electrons? 9. And neutrons, we don't really need them, but there are 10. Let's draw our Bohr model. Put our nucleus in the middle. 9 protons, 10 neutrons. First ring will hold 2 electrons. And we're not done, so we need another ring. How many are left? We need 9 altogether. That means we've got 7 left. 2, 4, 6, 7. In order to have full energy levels, how many electrons would hydrogen need in order to have that last ring or that last shell be full? Hydrogen wants 1 more electron because its outer shell is the first shell. It only needs 2 to be full. Then you look at fluorine. Fluorine's outer shell is the second one. That needs 8 to be full. And we've got 2, 4, 6, 7. So fluorine also wants 1 more electron. These two atoms can solve this problem by sharing their electrons between them. Hydrogen has 1 to share, fluorine has 1 to share, and out of that, they both feel like they have a full shell. Let's see what that looks like. So we'll start with our Bohr models, just like we did before. Here's hydrogen, 1 proton. Here's its first shell. It had 1 electron there. Then we had fluorine, which had 9 protons, 10 neutrons. Here's its first shell. This time we'll make fluorine's electrons white. There were 2 electrons there. And then it had its second shell, a little bit crooked there, and it had 2, 4, 6, 7. when you look at these two atoms and how they have come together to share electrons, the hydrogen can now feel like it has 2 electrons, these 2 right here, and 2 electrons in that outer shell makes it full, and the fluorine now feels like it has 8 electrons in the outer shell. 2, 4, 6, 8. So when these two atoms share electrons between them, they both feel like they have a full outer shell. That makes them chemically stable, and they form a covalent bond. Both of these are nonmetals. Remember, covalent bonds form between a nonmetal and a nonmetal. That's it for today.